Hello and welcome back. In this video we'll consider having other substrates other than alkyl halides for our substitution and elimination reactions. So some of the more common ones are alternative really good leaving groups as alkyl sulfonates. So alkyl sulfonates make really good leaving groups because they are resonance stabilized. This is called a mesylate here. We have a mesylate group because it's the sulfur with the sulfate group with the methyl here. And here we have a tozzolate group where we have this sulfonate group with this benzene ring with a methyl in the para position. And next we have the triflate group, which is the sulfonate group with the carbon trifluoride here. So methylates, tozzolates, and triflates make really good leaving groups, okay, for SN2 reactions. In other words, the nucleophile can come in and attack and kick out this leaving group very, very easily because they make really stable leaving groups. So we use these abbreviations OMS for mesylate, OTS for tozzolate, and OTF for triflate. And these are good leaving groups because they're resonance stabilized. See here, we have the same species but just different R groups. And so, based on the pKa values, the one that is the better leaving group is going to have the stronger acid is going to give us a more stable conjugate base. The more stable conjugate base is going to be the better leaving group. So here we have a pKa of negative 1.9, which is still really strong acid. Negative 2.8 versus negative 14. So the trifluoromethane sulfonic acid is negative 14. As for pKa, that's going to be the best leaving group. That thing is really gives us a stable leaving group, but it's a really strong acid. So we make these sulfonates on our substrate from the corresponding alcohol. Okay, so this alcohol will actually attack the sulfur, okay, kick out the chlorine, and then some pyridine acts as a base to pull off a hydrogen and give us the product. Okay, so that's how these are actually formed. And we'll study this a little more in the chapter on alcohols. Okay, but notice that alcohols are not good leaving groups. So we can use our alcohol as a starting material to form our tozzolate, and now we have a good leaving group. Notice we did not invert the configuration at the carbon bearing the alcohol when we form the tozzolate. That's because the alcohol is acting as the nucleophile. It's not getting attacked here, and so we don't get inversion at this point. The tozzolate retains its configuration. Okay. So alkyl sulfonates can give us SN2 products or E2 products. Okay, they can give us, depending on which we have. So with a strong nucleophile, strong base, a primary substrate gives mostly SN2 with a little E2, and we would have learned that from our chart. And with a strong nucleophile, strong base, a secondary substrate is going to give us mostly E2 with a little SN2, and that's because it's more sterically hindered. The SN2 is going to be more sterically hindered and a little harder to happen. Okay. So alcohols themselves can also be used to do substitution reactions. And so in this case, we have an alcohol that can give us, say, an alkyl bromide through a substitution reaction. In this case, this is a primary alcohol, and we're going to form the alkyl bromide by an SN2 reaction. Even though alcohols are not good leaving groups, the first step in this reaction would be to protonate this alcohol. So this is in acidic conditions. We've got HBr, which is a strong acid. We protonate the alcohol. Now we've got water as a leaving group. Water is an excellent leaving group. So now the bromide can come in and attack, kick out the leaving group, and give us our product, which is an alkyl bromide. Water was our leaving group, and that's going to be very stable. Okay, so, but if we have a tertiary alcohol, we're not going to get an SN2 reaction, so we can get a SN1 reaction, okay? And so the first step, again, is protonation, and then we're going to form our carbocation, which can be attacked by the bromine and give us the product, okay? So strongly acidic conditions are generally going to be, these are going to be protic, right? So this would favor an SN1, but since primary carbocations are unstable, even if you have a primary substrate, you can still get a reaction, but it's going to go through an SN2 mechanism. Alcohols will also undergo E1 elimination when reacted with sulfuric acid, and this is kind of an anomaly here. Normally we think of E1 as being having a, or elimination as having a strong base, but here we have an acidic conditions giving us elimination. So the mechanism is a little different here. We've got a tertiary alcohol, and our first step, we're going to protonate that. It's going to pick up a hydrogen from the acid, and then we can form our carbocation by that water forming as a leaving group. So this OH is going to leave instead as water, which is very stable for a leaving group. And then the mechanism is just the same as the other E2 mechanism, where a base is going to come in and pull off a beta hydrogen, giving us our alkene. So with sulfuric acid, we can actually get elimination, and this is going to favor E1 for secondary and tertiary substrates. So predict the major and minor product for each of the following reactions. So for A, we've got sodium ethoxide. Sodium ethoxide is a strong nucleophile and a strong base. We've got a secondary substrate. So looking at my chart, I see that E2, let me bring the chart over. I've got it on a PowerPoint here. For a secondary substrate, I see that E2 is going to be the major product, and SN2 is going to be a minor product with a strong nucleophile and strong base. Okay, so let's consider that. With sodium ethoxide, I've got E2. So this is Tazzalate. That's a good leaving group. That's going to be our major product. Sorry. And SN2 is going to be minor because the secondary is more hindered. So OET. And since we don't have stereochemistry here, we don't need to consider inversion of configuration, so we don't get a chiral product. Okay. All right, the next one, we've got a strong nucleophile, strong base, sodium hydroxide. I've got a Tazzalate, which is a good leaving group. And I've got a secondary substrate again. Okay, so that's going to give me E2 as major, SN2 as minor. So let's go ahead and draw that SN2 product first. Over here on the right. Now, this is a chiral carbon, and therefore the hydroxide is going to be on a dash, whereas the Tazzalate was on a wedge. So we're going to invert that configuration. This is going to be our SN2 product, and again, that is a minor product. Okay. Now, E2 is going to be major, but we have two beta positions here, so we have regiochemistry at both. Okay, so if we eliminate from the end, we get the Hoffman product. Okay, so that's going to be a minor product with sodium hydroxide as our base. If we eliminate from one of those hydrogens, we have two possibilities. We can get, right, is that right? Yeah. We can get the trans product, okay? And we can also get, drew that wrong. You can also get the cis product, and that would be like this. Okay, so our major product was E2, and these are both Zaitsev products. So Zaitsev is going to be major over Hoffman, okay? E2 predominates over SN2, so SN2 is minor. Zaitsev predominates over Hoffman, so one of these Zaitsev products is going to be major. Trans predominates over cis. So this is going to be our major product over here. Okay. And now I'm going to have to erase some of this if I'm going to do the next problem. Okay, so let me go ahead and do that, because I didn't give myself another whiteboard to work with. So this is going to take a minute, sorry. Alright, so next we've got sodium hydrosulfide. That NaSH is called sodium hydrosulfide, and we're working with a secondary starting material. So sodium hydrosulfide is a strong nucleophile, but a very poor base. Okay, it's not really a base at all. So we've got strong nucleophile, weak base, okay, and then we've got a secondary substrate. So looking at our chart, that's going to be SN2 only, okay? So our only product then, and we don't really have to worry about stereochemistry here again, because this is not a chiral center, okay? So we just replace that OTS with the SH. The next starting material, our OTS is right here. So that is secondary, okay? And sodium hydride is our reagent, and that is base only. Okay, so strong base, weak nucleophile, and secondary E2 is going to be our only possibility. All right, and so if we eliminate this way, we've got a hydrogen coming out here, but it is not anti-periplanar. Okay, so we have to have it anti-periplanar, and that means that this is going to be our only product. All right, next we've got Tazza chloride and pyridine, and then T-butoxide. So what is that Tazza chloride and pyridine step? That's the step to put on the OTS group. So in the first step, we're going to convert our substrate, and we don't change configuration here, into OTS. Okay. All right, and then the second step, now we've got T-butoxide. Okay, T-butoxide is a strong base. It's not a good nucleophile because it's so bulky. So for a secondary substrate, we can't expect substitution. Okay, so I wouldn't say weak nucleophile, but poor nucleophile. Strong base, poor nucleophile, and secondary substrate is going to be E2 only. So we could eliminate from this side over here on the left, or we've got one hydrogen on the right, okay? So our Zaitsev product is going to be this. We only have one possibility here. And our Hoffman product is going to be this. Again, just one possibility, okay? So those are our two products. Next, we've got Tazza chloride and pyridine again. So we're changing this OH into an OTS in the first step. Let's just draw it over here because we're running out of space. Our second is sodium ethoxide. So this is a primary substrate, and sodium ethoxide is a strong nucleophile, strong base. With a primary substrate, SN2 predominates just because it's faster, because we don't have any that steric hindrance here. So our major product is going to be this one, OET is going to be our product, and our minor product is going to be the elimination product here, right? So we eliminate, we're going to pull off one of these hydrogens over here, we're going to form a double bond right there, okay? So that is our product of elimination. With primary, SN2 predominates, so this is major, okay? All right, so thanks for watching. I think we've got one more video in this series, and I'll see you in the next one.